right. So we're going to start with question number 1. And again, this is the nomenclature section of the ACS study guide. And you can buy an ACS study guide for $25. I recommend buying one if you're interested in writing a standardized exam that involves organic chemistry. It can be very useful. Anyhow, first question is, what's the IUPAC name for this compound? We can clearly see that it is an alcohol. And what's the rule for naming an alcohol? We want to find the longest carbon chain, and we want to number it in such a way that we give the hydroxyl the lowest possible number. So we would start numbering from what is the right-hand side, the way it's written. So we have 1, 2, 3, right? If we were to go from this side, we'd have 1, 2, 3, 4. So we would have a 4-hexanol, and a 3-hexanol is preferable. So 1, 2, 3, 4, 5, 6. So we know this is some kind of 3-hexanol, and you can see that that's the only answer that has 3-hexanol. So it's got to be the right answer. And then we also see that we have the 5,5-dimethyl on there, and so the answer to number 1 is B. Well, let's take a look at another question here. And question number 3 just asks us, which compound is E12-dichloro-2-pentene? The easiest way I think there is to solve a problem like this is to start with E or Z, right? Because if we have some compounds that are Z, we could just, nix those right away. If you look at the first compound, in A, you have the chlorine, which takes precedence, and you have this ethyl group, and so those are E to each other. So this is an E compound. It's a possibility. Whereas in B, you have the chlorine and the ethyl on the same side, and those are zusammen. This is Z, so we can cross that one off. C is also an E compound, right? You can see that these two groups are the highest priority groups, so this is also an E compound. And then D, you can see you have the two protons cis to each other, so this is definitely a Z compound, so we can cross that one off. So now it comes down between A and C. Which one of these compounds is it going to be? Because it's, oops, I crossed off the wrong ones. Because it's got to be an E compound. So we'll cross it with 2 Z compounds. There we go. Well, I think the next thing to do would be to look at the parent chain and look for a 2-pentene. You can see that in A we have 1, 2, 3, 4, 5. So this is a 2-pentene because the double bond starts on carbon number 2. In C we have 1, 2, 3, 4, 5. And so the double bond starts on carbon 3. And so we can cross this one out. And that means that it must be A. And if we double check the placement of the chlorines, you can see that we have a chlorine on carbon number 1 and a chlorine on carbon number 2. So A is E12-dichloro-2-pentene. Let's move on to question number 4. Here we're naming a ketone. We're just asked to name this guy right here. It says, what is the IUPAC name for this structure? I'm going to give you a couple seconds to look at it. And if you think you have an answer, feel free to throw it up in the chat. Does anybody have an answer for this one? We have a ketone here. Yeah, the answer I think is C as well, right? Absolutely. All of my students who are answering are 100% correct. What's the giveaway? I think that the easiest way is to recognize that we have the longest carbon chain here, right? We number it in such a way that we give the carbonyl the lowest possible number. 5, 6, 7, or 5, 6, 7. There we go. So this is a 3-heptanone, right? You can see that these two compounds aren't even named correctly because they don't have a locant for the carbonyl, right? There's nothing here and there's nothing here. So we can cross A and B right off the bat. And you can see that in D, they've numbered it the wrong way, right? They've gone 1, 2, 3, 4, 5. Yeah, they've gone the wrong way. And so here we have the 5-bromo, we have the 4-methyl, and it's 3-heptanone. There we go. Awesome. Awesome work. And you can see that you can solve a lot of these problems by process of elimination. Let's take a look at question number 5. It just says, which is the structure of Z 3,5-dimethyl 3-nonene? You know what? I'm going to give you guys a second to take a look at it and see if you can come up with an answer. Just imagine you're on that exam. And sorry, you can see some of my pencil work in here. Came out when I tried to scan it. Yeah, I think we're on the right track here for sure. A problem that I notice in A right away is that if you look at this carbon, okay, this carbon right here, we have a methyl group here and a methyl group here. So for this one, there's no E or Z, so we can cross this one off immediately. If you look at B, you can see that the highest priority group is here, and the other highest priority group is there. We have a hydrogen here, and so this is an E compound, so we can cross this one off the list. If you look at D, you can see that this is also an E compound, right? How do I know? I have the ethyl group, which is higher priority, and I have all this group over here and a hydrogen here. So this one we can also cross off the list. Whereas if we look at C, which we know again is the right answer, you can see that if we have our longest carbon chain, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is some kind of 3-nonene, which is good. We have methyl groups at carbons 3 and 5, also good. And we know that this is a Z compound because the ethyl group has the highest priority, and then this group here has the highest priority. They're on the same side of the double bond. And so this is, in fact, a Z compound, and this is the correct answer. Great work. Excellent. Well, let's move on from there, staying in the nomenclature vein for a few more minutes here. And we're going to take a look at question number 7. Again, this is just the regular old ACS study guide. Now, we don't look at a ton of bifunctional compounds in this class. We don't look at, Avogadro's number of bifunctional compounds, meaning we have an alkene and an alcohol. But something that I did mention to you several times in the class is that based on the hierarchy of functional groups, which I did have in my slides, that whenever you have a functional group that has an oxygen in it, it's going to take precedence over something like just a double bond or a triple bond, for example. So this compound is an alcohol, and we can see by the suffixes here that the compound is definitely an alcohol because all the suffixes end in "all." Now we're going to number the longest carbon chain, which would be this one here, so that we give that hydroxyl the lowest possible number. So we go 1, 2, 3, 4, 5, 6, 7. So this is some kind of 2-heptanol or heptan 2-all, as you see in these ones here. We don't see that here. We don't have the right number of carbons in the chain. And here they've numbered it incorrectly. So now that it comes down to C and D. Well, is this an E or a Z compound? You can see that the ethyl group is going to take precedence, and this group is going to take precedence, and they're on the same side of the double bond. So this is a Z compound. And this locant here, I just want to point out that this 4-heptene, the 4 here represents where the double bond starts, that it starts on carbon number 4. And so D is the correct answer here. So this is Z5-methyl 4-heptene 2-all. But again, this shows you how you could solve a problem just by process of elimination using, what you know about organic chemistry. And you'll be expected to be able to apply your knowledge. And especially anybody who's interested in writing a standardized exam in the future, you'll definitely be asked to apply your skills in those kind of exams. Well, here we have another question. This is a really good one of my favorites. Says, what's the IUPAC name of this compound? Well, here we have another bifunctional compound. The carbonyl is going to take precedence over the double bond, over the alkene. Why? Because the carbonyl has an oxygen in it. And I told you, anytime you have a functional group that has oxygen in it, it is going to take precedence over something like a double bond or a triple bond, okay? So this compound is some kind of ketone, right? Now, if we just had the carbonyl, then it would be cyclohexanone, right? But since we put the double bond here, we want to give that double bond the lowest possible number. We assume that this is carbon number 1, or a carbonyl carbon. So we have 1, 2, 3. So this is a 2-cyclohexenone, right? It's a 2-cyclohexenone because we have cyclohexanone, but then we have cyclohexenone over here, and this locant represents where that double bond is, right? So we number the compound like this: 1, 2, 3, 4, 5, 6. We have the isopropyl at carbon 6, and we have the methyl at carbon number 3. So our methyl's at carbon number 3. And you remember that even though this is an isopropyl group, we can also use the systematic way of naming it, right? And we did discuss this in class. We said we take the longest carbon chain, so this would be an ethyl, And then whatever groups are attached to that, which is a methyl on carbon number 1, we give those an identity. So we have 6-methyl ethyl, right? We don't have to call it 1-methyl ethyl, because if it was over here, right, if the methyl group was over there, then it would be a propyl group, okay? So then it wouldn't need some kind of systematic name. So there we go. The answer is D in this case. Let's move on to the next section, which deals with hybridization and resonance and aromaticity. And I have a question for all of you, okay? So if you're like, oh, I'll just watch the video later, you can just wake up and I'm sure you're all awake. But anyhow, I would like you guys to try to answer this question. This goes all the way back to chapter 1 of Organic Chemistry 1. What's the hybridization of the orbital containing the unshared pair of electrons on the nitrogen atom of pyridine? Can anybody tell me the answer to this one? This is something that we looked at in chapter 1, and we talked about it in detail. Hot diggity darn. That's right, Jisoo, 100% correct. It is sp2 hybridized. And again, if you don't follow me on that, you might want to go back and take a peek at that in chapter 1, because we said, well, if you look at the structure of the aromatic ring, so I got to go back here. Okay, if you look at the structure of the aromatic ring, it is planar. So I'm going to try to draw it like this, right? And you have the nitrogen here, the double bond here, here, here. So that means you've got p orbitals here, 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 right? Every atom has a p orbital on it because the compound is aromatic. So that lone pair is in an unhybridized sp2 orbital, right? You have that continually overlapping system of p orbitals like that. So that already means that there is a p orbital on the nitrogen. Therefore, since the steric number is 3, that lone pair is sp2 hybridized. So again, this was covered at the end of chapter 1 in Organic Chemistry 1. Let's take a look at a question that I think that everybody would get pretty quickly. Not that we're into, answering everything in hyperspeed, but I'd like to ask you question number 7. It just says, what are the hybridizations of atoms 1, 2, 3, and 4? If anybody has an answer for this one, feel free to throw it up. All right, I think my students are all on the right track, right? Number 1 is sp2 hybridized. That means it's got to be either this one or this one. The second one is sp3 hybridized. So you can see it's got to be B. Let's double check. Number 3 is sp2 hybridized, so that works out. And the oxygen here in the alcohol is sp3 hybridized. And there you go. So make sure you know about steric numbers and hybridization, but it seems like you guys are pretty quick on that, faster than I am. I have a question, which is question number 9. Yeah, that's my finger here from when I tried to scan. Anyhow, it says, for which free radical out of these 4 free radicals can the most resonance forms be written that show the delocalization of that radical? Most resonance forms. Could anybody tell me which one of these you could draw? The most resonance structures, you'd need the bigger piece of scratch paper to sit there. Yeah, the answer is D, and the reason why is because not only is it benzylic, but it's doubly benzylic, right? If we look at C, this is benzylic, so we could start by writing, I could make that better. There we go. We could start by, drawing resonance structures like this, and there's nothing wrong with that. But in D, we have doubly benzylic. So here, this is benzylic, but this one is benzylic times 2, okay? So we could, son of a gun, why does it keep doing that? There we go, and so on and so forth, and we could draw all the different resonance contributors. So this one would have a total of, C would have a total of 4 resonance contributors. Make sure you can draw them. And D would have a total of 7 resonance contributors. Make sure you can draw those. B is vinylic. That is so unstable. So vinylic, you're not going to see vinylic radicals in organic chemistry. Let's move on to question number, let's go to question number 12. So question number 12, it just says, which of these structures have 8 pi electrons? I'm going to ask you a different way. Which compounds are aromatic? Could anybody tell me which compounds here are aromatic? So I'm not sure if you're answering my question or anyhow, the compounds that are aromatic, okay, would be compound 2 is aromatic and compound 3 is aromatic. Right? You'd have this lone pair on this nitrogen that would participate in aromaticity, and you'd have this lone pair on the sulfur that would participate in aromaticity. So those two compounds are aromatic. So we'll put here aromatic. Okay, they both have a Huckel number of pi electrons, which is 4n plus 2, where n is equal to 1. So that's good. But one of these has to have 8 pi electrons, and the answer is only this one, right? Number 1 has 8 pi electrons, right? We have 2 here in this double bond, 2 here, and 2 here. So those are all considered pi electrons, but that molecule is not going to be, it's not going to be an aromatic compound because it doesn't have a Huckel number of electrons, but it does have a total of 8 pi electrons. Let's move on to question number 14. Could anybody tell me this one's not that simple, I don't think. Question number 14 is definitely doable. Could anybody tell me which one of these structures would be considered aromatic, if any? Well, number 1 is definitely going to be not aromatic, right? This is the cyclopentyl cation, which is anti-aromatic, okay? Because here, this compound is anti-aromatic because you have a 4n number of pi electrons where n is equal to 2, or sorry, where n is equal to 1. So we have a total of 4 pi electrons, right? Because we have a p orbital here, because that carbon is sp2 hybridized. We have another p orbital here, 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 and here, and here, and here. And so that's going to be an anti-aromatic compound. And number 2 and number 3, those are both aromatic compounds, aren't they? Right? These are both aromatic. And so the answer is 2 and 3 only. Why? Because these both have a Huckel number of pi electrons, 4n plus 2, or n is equal to 2. Right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons here. And it's easy to see why this molecule is aromatic. Naphthalene is completely planar. Right? But here, if you put both of these lone pairs in a p orbital, look, if these were in unhybridized p orbitals, then you would have a continuously overlapping system of p orbitals. Forgive me for my artistry here. Then you have a complete conduit, and you have a Huckel number, right? You have a total of 10 pi electrons. Let me prove it to you. Look, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is a Huckel number. And so number 3 is also aromatic. Let's try number 15. This one's kind of a quick one. Could anybody tell me which one of these is not aromatic? So that means that all of them are aromatic except one. D is definitely aromatic. The cyclopentenyl cation, right? Because this is 4n plus 2, or n is equal to 0, and you have sp2, sp2, and sp2. So this is definitely aromatic. It's going to be A, right? Because there's no electrons on boron. Right? Boron is in group 3A, therefore it has no lone pair, and so therefore this compound is not aromatic. And we could put here no lone pairs. Okay, whereas C and B are both aromatic. So this one is called the tropylium cation. Am I spelling that correct? I don't know. I gotta double check. Yeah, it's with a Y. That's what I thought. There we go. The tropylium cation is aromatic. Okay, and this compound is aromatic too. You put these and a unhybridized p orbital, then you'd have 1, 2, 3, 4, 5, 6 pi electrons, continuously overlapping system of p orbitals, and it's planar. There we go. So everything is aromatic except A. Okay, let's try. Could anybody tell me in 16 which one of these carbocations would be the most stable? So I'm looking for the most stable carbocation out of all of these. Yeah, I tend to agree with you, right? If you look at A and C, they're both benzylic carbocations, right? So you could draw resonance structures, right? You could draw delocalization and you could draw resonance structures for this, or you could do it for this one too. However, the first one in A is secondary benzylic, so this is secondary and benzylic, and this one is only primary and benzylic. And so the secondary is going to be a more stable carbocation. And so the answer is A, secondary and benzylic. Let's take a look at acids and bases. Talk about acid-base chemistry. What are we looking at here? Let's see. It says, which structure corresponds to the predominant form of this molecule, which you can clearly see is an amino acid. This is alanine. Okay, and again, I don't expect you to memorize all the amino acids, but if you're at pH 7, it says near 7, so that means it's close to physiological pH. Could anybody tell me which one of these forms of the molecule would predominate at around physiological pH, which is around 3 or 7.35 to 7.45 ish? Yeah, the answer is definitely C, right? We covered this recently. Okay, now the reason why is because we know that the pKa here is pretty low, and since we're in a more basic environment, it's going to deprotonate, whereas the pK of this nitrogen, or the pK of the protonated form here is around something like 9 or 10, and so at a pH of 7, it's going to be protonated because we're in a more acidic environment. So we end up with the Zwitter ion. So Zwitter ion. Like that. Again, I could scribble this in here. So the pK here, pKa is around 5, and the pK here is around 9-ish. So since 7 is in between, again, it's more basic than the pK of the acid, and it's more acidic than the pK of the amine. There we go. So we have the Zwitter ion. Let's take a look at number 2. Which is the strongest base? Right, you have all these different compounds. We want to know which one is the strongest base. It's not a difficult question. This one's kind of a short question. There's one of these compounds that's very different than all of the others. All right, if we view these as bases being a proton acceptor or an electron donor, right, an electron donor, that's the Lewis definition of a base. Now we know that amines are bases, right? We have a lone pair here, we have a lone pair here, we have a lone pair here, and then we have a lone pair down here. But one of these lone pairs is much more available than all the other ones. Right, if you look at all the aniline derivatives, with all those, you can draw resonance structures where you put the lone pair inside the ring, okay, where it's delocalized inside the ring. But on this one here, this is not an aniline derivative, and that lone pair is localized. So this one, the lone pair is localized, whereas all of these are delocalized. Now, if they're delocalized, how available are they going to be to accept a proton or donate a pair of electrons, however you want to view it. They're not going to be nearly as available as A, where the electrons are localized and they are available for donation. And so A is going to be a much stronger base than all the rest. All right, it's going to have a much higher pKa than the rest of them. All right, let's see. Let's try number 3. Number 3 is one I would expect you all to get, you know, in a relative short amount of time. It just says which carboxylate is the strongest base. You got 4 carboxylates, all 4 of these beauties right here. Could anybody tell me which one of these would be the strongest base? Yeah, it's going to be A for sure. Right? Now, in terms of strongest base, we could think, well, the strongest base is going to be, these are all conjugate bases of carboxylic acids. That means the strongest base is going to come from the weakest acid, right? So weakest conjugate acid. So if you think about the conjugate acid of all these, if you just scribble in a proton, right, which one of these would be the strongest acid? This one would be the strongest acid, right? Because it's got the inductive effect of 2 chlorines. This one, so we'll call that the strongest acid. This one would be the second strongest acid because it has only 1 chlorine. This one would be the third strongest acid, right? Because it's got 1 chlorine, but it's beta to the carbonyl, right? This one is alpha, this one is beta. These are both alpha. And this one has no electron withdrawing groups, right? It has no inductive effect. And therefore, this one is going to be the weakest acid, okay? Therefore, the conjugate base is going to be the strongest base. So strongest base. Give me a thumbs up if you follow me on that one. A little bit of acid-base chemistry for you there. And just the rationale. So, you know, when we're thinking about aereo, atom, resonance, induction, orbital, we couldn't use atom because the negative charge is on an oxygen in each case. We couldn't use resonance because they all have the same resonance structures for the carboxylate, but we could use induction, couldn't we? Right, and these 3 all have inductive effects, whereas A has no inductive effects, and therefore that's how we're going to differentiate between the relative acid-base strength. All right, let's move on from there. And let's try number 9, because we spent some time talking about aromaticity. It says the imidazole ring system, which is shown right here, contains 2 nitrogen atoms found in the amino acid histidine. Good. Which statement is true regarding the basicity of the 2 ring nitrogen atoms? So this one has a lone pair on it, and this one has a lone pair on it. It says both are strongly basic. And B, the nitrogen atom labeled 1 is more basic than 2. C, the nitrogen atom labeled 2 is more basic than 1. And neither nitrogens would be considered basic. Could anybody tell me what the correct answer for 9 would be? Yeah, I agree. The nitrogen atom labeled 1 is going to be more basic. Why? Because this lone pair, right, is not participating in aromaticity, whereas these ones here are participating in aromaticity, right? The ones on number 2. Remember, when you have a lone pair and a double bond, a pi bond on an atom, both of them are not going to contribute to aromaticity, right? And so the lone pair that I have circled in green is going to be basic because it's not participating in aromaticity. All right, let's take a look at some questions that involve stereochemistry. So stereoisomerism, I wanted to look at question number 5. It says, which of these molecules are mesoisomers? I'll give you a second to look at it. Anybody could tell me which one of these are meso? Yeah, I think the answer is B as well. I think it's only going to be the second one. Because when you have a compound that's meso, you've got to have greater than or equal to 2 stereocenters. So you've got to have a couple of stereocenters, and you've got to have a plane of symmetry. Plane of symmetry. Well, if you look at 1, there's no stereocenter in this molecule. So no stereocenter. Stereocenter. If you look at number 2, we have a stereocenter here and a stereocenter here, but we also have a plane of symmetry running through the molecule. In number 3, there are 2 stereocenters. Yes, there are 2 stereocenters, but there's no plane of symmetry in this molecule. And so the answer is only the second one has a couple of stereocenters, but it is an achiral compound because it won't rotate plane polarized light. Okay, let's try question number 9. It just says, what would be the stereochemical classification of the product of this reaction? You take 2-butene, you hit it with some HBr. You don't even have to worry about Markovnikov or anti-Markovnikov. A racemate means the same thing as a racemic mixture. Racemic mixture. Could anybody tell me which one of these you'd end up with? Yeah, I agree. I think you would end up with a racemic mixture. Now, why would that be? Because it doesn't matter if it's cis or trans. I'll just draw it as trans 2-butene. When it reacts with the HBr, what do you end up with? Right? You end up with a carbocation. And we know that carbocations are trigonal planar, right? This is trigonal planar. And so the bromide can come in and it can attack either face of the molecule. Right? It can attack from this side or it could attack from this side. And so what we end up with are 2 compounds. We end up with this compound and it's enantiomer like this. So we end up with a racemic mixture, so a racemate. And again, the relationship between these 2 compounds is that these 2 compounds are enantiomers. All right, good, good. Let's try question number 10. It's a really fast one. You have 4 diastereomers here. They're all isomers of each other. So they're just asking you which diastereomer would be the most stable out of these 4 diastereomers. Could anybody tell me which one of these would be the most stable? Yeah, I think it's going to be B as well. Right? I think the answer would be B because all substituents are what? Equatorial. Equatorial, and there are no 1,3 diaxial interactions. Interactions. All right, and you can see the 1,3 diaxial interactions here. You can see them here, and you can see them here as well. But in B, we don't have any of those to be concerned with. Okay, let's take a look at question 11. Where is it? It says the product of this reaction will be achiral, not meso, mixture of diastereomers, a meso compound, or a racemate. I'll let you think about it. I'm going to draw a partial mechanism here. Yeah, I agree with you, right? Because this is a Markovnikov addition. So you would end up with this carbocation, which is not going to undergo any rearrangement. And then after the chloride comes in and acts as a nucleophile, so let me fix that up. There we go. You're going to end up with a compound that has no chiral centers. So it's just got a methyl and a chlorine. And so the compound is achiral, but it's not a meso compound, is it? It's got no stereocenters in it at all. So the compound is achiral, but not meso. Let's take a look at question number 20. So I'm going to move ahead to question number 20. Question number 20. Cyclohexene reacts with bromine to give 1,2-dibromocyclohexane. Molecules of this product would be what? Well, let's see. If we have cyclohexene as our starting material, when we react that with bromine, could anybody tell me, is this an anti-addition or a syn addition when I add bromine across that double bond? It's anti-addition, right? So I would end up with this compound, plus I would end up with the enantiomer. So I end up with a racemic mixture. So you see that answers A and B both say racemic, whereas C and D say a meso compound, and we would not get a meso compound. So we've got A and B. I'm going to give you guys a second to read the whole answers. And could anybody tell me, would it be A or B? One bromine axial, one bromine equatorial, or both equatorial? Yeah, it's going to be A, isn't it? They're both going to be equatorial, right? Let's say I drew a chair and there's not a lot of room to draw a chair. I'll draw it over here. There we go. Find my pen. There we go. Okay. So if we draw the ring like this, okay, let's say we have this bromine here is going down in its equatorial. This bromine is coming up. Well, it's going to be up and equatorial. And so there you go. It's going to be racemic, right? You're going to end up with a racemic mixture, but both bromines are going to be equatorial. And there you have it. Okay, let's try one more from this section. This is question number 25. Which reaction would yield a meso product? So we have the same starting material, which is just cyclobutene. And you can add water, HCl, bromine, and deuterium. So D2 is the same thing as adding H2 to the molecule. So it's like adding hydrogen. Where am I here? I lost the question. Come on, question. Where are you? There we go. So question 25. So D2 is the same thing as doing a hydrogenation, but you can't leave the deuterium out. You would have to draw it. Yeah, I agree with you. I think it's D because of syn addition as well. I'm going to switch over to a blank document just for a second here. We're going to take a look at the question in detail. So this is question number 25 from the ACS study guide. So in A, we took cyclobutene and we treated it with water and acid. So that's just going to be a Markov-Nikov addition of water, but there's no Markov-Nikov or anti-Markov-Nikov to worry about. So you would just end up with cyclohexanol, which is not a meso compound, right? It's achiral. Then if we look at B, we do the bromination. So we're treating cyclohexene with bromine in carbon tetrachloride, which is just the solvent. And in that case, we discussed this a few seconds ago, you would end up with a racemic mixture, right? You end up with this plus the enantiomer. In C, you're doing another Markov-Nikov addition. It's a hydrohalogenation with HCl. So you would end up with this compound, which is achiral. But indeed, we know that hydrogenation is syn addition, right? So if you replace the H2 with D2, remember that deuterium is just an isotope of hydrogen. Deuterium is equal to hydrogen 2, okay? So, and we're using platinum. So what we would end up with is this compound where we have one deuterium and the other deuterium like this. And so this has a plane of symmetry running through it like this. So this actually is a meso compound like that. So the answer is D, which is a meso compound. All right. Let's take a look at some questions that deal with nucleophilic substitutions and eliminations. Just give me a second here. And I thought we'd start by looking at question 1. And it simply says, which reagents could be used to make this compound? I want to make this compound right here. which is 2-hexyne. Could anybody make a suggestion about this one? There's a problem here with a couple of these, aren't there? Right? If we have 2-hexyne, that means we have a total of 1, 2, 3, 4, 5, 6 carbons. Well, if you look at B, B is set up to do an SN2 reaction, right? If you were to do nucleophilic attack and loss of leaving group like this, but then you have 1, 2, 3, 4, 5 carbons, so that can't be it. If we look at C, similar thing, we're set up to do an SN2 like this. However, then we have 1, 2, 3, 4, 5, 6, 7. So that's got too many carbons. The problem with D is that there's no nucleophile and no electrophile. That's just 2 hydrocarbons mixed together. That's not going to be doing anything at all. Whereas in A, we're perfectly set up, and forgive me for this very short sigma bond here, but I'm just trying to show you that this is set up for a beautiful SN2 reaction like this to give us our desired molecule, which is 2-hexyne. All right, let's turn our attention to question number 6. Let's see, question number 6. It says, what would be the major product of the dehydrohalogenation of 3-chloropentane by potassium hydroxide? So we're starting with 3-chloropentane, which is this molecule, and we're treating it with potassium hydroxide, and we're doing a dehydrohalogenation. So that means we're going to lose HCl. Well, this is my alpha carbon here, and I've got 2 beta carbons. They're identical though. So really I've only got one kind of beta proton that I'll draw in here. All right. So what's the major product going to be? The major product is going to be this, where I have this, which would be 2-pentene. Now here I've drawn it as trans 2-pentene, but you can see there's no trans or cis for any of these compounds here. And so which one of these is the correct compound? The correct compound is D. This is 2-pentene. Let's try question number. Let's go to question number 12. Ooh, here we go. It says, which one of these would not be likely to undergo a rearrangement? Think you have an answer? Just throw it up there. I see a letter up there, but I'm not sure if that's new or old. So. Okay, there we go. All right, yeah. So if we look at A, this is a secondary carbocation, which could undergo a hydride shift, couldn't it? Oops. This could undergo a hydride shift to give us this, right, where we would have something that looks like this. Okay, and then we would go from a secondary carbocation to a tertiary carbocation. And again, this is a hydride shift. The next one is secondary. Okay, and this one could undergo a methide shift or a methyl shift like this, and then that would give us something that looks like this, where we have CH3, CH3, yeah, and then we'd have this. So we go from something that's secondary to something that is tertiary. So that's going to undergo a hydride shift, or a methide shift rather. This one is tertiary. There's no reason for it to rearrange whatsoever. Whereas this one here, the last one, if I just draw this hydrogen, if I draw this hydrogen out explicitly, right, this one could shift over here, draw a better arrow than that, right, and then I'd end up with this, which would be a tertiary. This is a terbutyl cation. Okay, so then we would go from something that is primary to something that is tertiary. So that's definitely going to undergo that hydride shift. Okay, so the answer is C. It's the only one that's not going to undergo any kind of rearrangement to produce anything more stable. All right, number 16. We're going to do an elimination reaction, right? It says we're going to do a dehydration of this alcohol. So we're going to end up losing water. And it says, which alkene is likely to be formed in the largest quantity? So I think the best thing to do with this question would be to write it out completely and draw a mechanism for it. So let's take a look at what the mechanism would resemble. So let's go over here. So this is question number 16, I think, from nucleophilic substitutions. With this molecule, just give me a second to draw it here. Starting with this alcohol. Here's my hydroxyl. And then I have a methyl group over here. Okay. So what's the first thing that's going to happen when we put this in sulfuric acid, H2SO4? All right. We know that we have a poor leaving group, but we're going to convert that into a good leaving group by a proton transfer. I'm going to not draw the proton transfer out. I'm just going to start by converting this into a good leaving group. So that's going to leave. Okay, so I've kind of skipped the proton transfer just to make things a little bit quicker. Okay, so now I'm going to copy and paste this to make it even faster. So I'll copy this. I'm going to paste it over here. And there we go. I didn't give myself enough room. But anyhow, you get the idea. So we end up with a carbocation. So let's draw that carbocation. Now you can clearly see that this is a secondary carbocation, but it can undergo a methyl shift like this to give us a more stable carbocation, can't it? Absolutely. So let's draw what that carbocation would look like. Now we've got a tertiary carbocation right here. So let me just make sure everything's good here. There we go. And the last step is going to be the proton transfer to make the alkene. Well, here's my carbocation. I've got beta carbons here, and I've got a beta carbon here. Let me use a different color. But if you were to remove the proton from the carbon that I have labeled in red, that would give you the Hoffman product. It's just not going to be the major product of this E1 reaction, because E1 reactions will preferentially form the most substituted alkene. And so we're going to end up forming the double bond right here. So what's the product we're going to end up with? We have our two methyls and our double bond right here. Then we have another methyl group here, and then we have this. So this is going to be the the final product, this compound right here, which is B, I think, if we go back and take a look. So you've got to know that this is an E1 reaction. The rearrangement is going to occur right here to make the more stable carbocation. And then you're going to eliminate this beta proton to make the most stable alkene, because that's what happens in an E1 reaction. So let's go back here. Boop. Is it question number? With this. There we go. So the answer is, is B. That's going to be the alkene that's going to be formed in the greatest amount. All right, so that's a good example of a question where I think it would be really handy to actually draw out a mechanism. Let's take a look at question number 17. I'll just throw this out there to my students. What would be the first step in the dehydration of cyclohexanol in sulfuric acid? So if we take cyclohexanol, right, and you treat this with sulfuric acid, and it says it's a dehydration, so we're losing water, we would end up with cyclohexene. Yeah, it's going to be protonation of the alcohol, isn't it? Didn't we see that in the last question? It's going to be protonation of the alcohol to convert it into a good leaving group. Then that's going to leave. So the first step is going to be protonation of the alcohol. So you can see how they love to ask questions about mechanisms in your knowledge of mechanisms in ACS type exams. Let's take a look at question number 20. Question 20 says, which of the mechanistic steps shown is not reasonable for the mechanism to describe the formation of 2-methyl-1-butene by dehydration of 3-methyl-2-butanol? One thing I noticed with this problem is they're asking you to make a Hoffman product, but hey, you got to know where Hoffman products come from too. So can anybody tell me which one of these just looks unreasonable? For this conversion, we're trying to go from here to here. Don't think about making Hoffman products, or sorry, Zaitsev products, because that's not what the question is about. The question is about making this compound. Exactly. The answer is C, right? Because you're forming a double bond. I'm going to write it out at C. The double bond is supposed to be here, so you have no reason to make a primary carbocation there. Everything else is totally reasonable. The protonation and loss of the leaving group to make the carbocation, that's good. The hydride shift, which is going to have to occur to make this carbocation, and then in order to make the Hoffman alkene, you'd have to pull off this beta proton. It's not going to be the major product, but that's not what the question is about. It's asking you about which one of these mechanisms is good to make this compound. And you can see that C is the right answer. That has no business, or has nothing to do with this reaction whatsoever. What's this? Question 24. Yeah, okay. Let's say we wanted to make this ether. Okay, so let me draw the bond line structure of this ether. We have an ethyl group over here. So you want to make tert-butyl ethyl ether, which is, again, this compound right here. Which one of these reactions would be the best way to do it? There's one of them that is definitely the best. Yeah. Right. Definitely. I see a major problem with A. In A, you're taking a tertiary alkyl halide, and then you're just treating it with a strong base. So that's just going to give you elimination. So in the first one, let me just erase this. Okay. In the first one, you're only going to get E2 product. So you would actually only end up with this compound. You'd end up with isobutylene. The next one, you have a Grignard, which is a really strong base. It's also a good nucleophile, but there's no electrophile here. So that's just going to do a proton transfer, and you're just going to end up with ethane, and that's not useful at all. In C, you have a strong base, strong nucleophile, and you've got a primary alkyl halide, and so that's just going to do the SN2 reaction, isn't it? Right? The nucleophile is going to attack the electrophile. You get the loss of leaving group, and that is going to give you the desired product. So the answer is C. And then D is similar to B, right? A Grignard is such a strong base. All it's going to do is a proton transfer, and you're just going to end up with, isobutane, okay? And that's it. So that's not very useful chemistry now, is it? All right. There we go. So C would be the best answer here. Let's take a look at question number 31. Where is it? Question 31. This is a good one. I really like question 31. It just tests you on your knowledge of E2 reactions. It says, which is the proper representation of the flow of electrons in this E2 elimination? I'll let you take a second and look at it. Yeah, the answer is A, isn't it? Right? Because you have the proton transfer, right? And you have the loss of leaving group happening at the same time. You can see there's something really jacked up about B. I mean, why would you start with a tail of a curved arrow on an atom and then end up on a negative charge, right? That is just really wacky. Okay, this is a leaving group. There's no reason why you would ever draw an arrow like this. That's not going to happen. If you take a look at C, there's also some really wonky arrows here. I mean, this is a good nucleophile, but why would it attack this carbon? Because there's no, or this doesn't represent an elimination, because the tail of the arrow isn't ending up on a proton, okay? It would have to end up on a proton like this. So that's incorrect. Okay, I'll cross that one off. And in D, this is showing a first order reaction, right? It's showing the loss of leaving group followed by the proton transfer. But remember, it says that it's E2. So if it's E2, it's E together. Everything happens at the same time. And so the correct answer is A. All right, I want to take a look at one more question from this section, which is, what is the major product of this reaction? We have this alkyl halide here, and we have a stereocenter here, and we have another stereocenter here, and we're treating that with potassium hydroxide. This is a tertiary alkyl halide, so this is going to be an E2 reaction. And since we have two chiral centers, this reaction is going to be stereospecific. Okay, now we went over this in Organic Chemistry 1, but I want to review it with you one more time. And that is the fact that the bromine, okay, if you look at it here, this bromine and this hydrogen have to be anti-periplanar to each other in order for this elimination to be effected. So what I'm going to do is I'm going to rotate this bond. I'm going to put the hydrogen over here. I'm going to put the methyl down here, and I'm going to put the phenyl group up here. And then we're going to redraw the sawhorse and see if we can figure out if we end up with an E or a Z alkene. So let me just erase the word stereospecific, and I'm going to redraw the sawhorse, which is going to look like this. I've still got my bromine here, my methyl group. I didn't change anything on the first one. C6H5, that represents a phenyl. Now in the back, I've got my phenyl over here. I've got my proton, anti-periplanar to the bromine, and I have my methyl group down here. So now you can see that the bromine and the hydrogen are anti-periplanar. Your base, which is the hydroxide, would come in, it would rip off this proton, you'd form the double bond, and you lose the leaving group like that, and then we end up with an alkene. And you can see that in that new alkene, because the double bond is going to be right here, you have a phenyl group going up here, you've got a methyl group coming down here, you've got another methyl group coming up here, and a phenyl group going down here. So the answer has to be either C or D. Those are the only correct ones. And again, you can see that this is an E compound or a trans compound. And so the answer is going to be C. Now, I know that in Organic Chemistry 1, I showed you how to do this by drawing the Newman projection. So you'd actually look down the carbon-carbon double bond with your eyeball, and you would draw a Newman projection. And there's nothing wrong with doing that. That still stands. I haven't changed my approach. You can still do that. But I'm just showing you how to do it just by rotating the bond in the sawhorse structure.